Hello everyone, I am Xinfeng from the USSLAB Zhejiang University. Today I am going to introduce our work, Learning Normality is Enough, a software-based mitigation against the inaudible voice attacks. Voice assistants such as Siri, Azure, and Amazon Echo are everywhere and make our lives easier. They can take the user's command and execute it. For instance, even open the door. So their security is very important. One of the main threats against the voice assistants is the inaudible voice attack, particularly the dolphin attack, which can enable the attackers to secretly inject the inaudible voice commands and even control the smartphone at 20 meters away. Let's look at this video. Thus, the goal of our work is to detect dolphin attacks. There have been two categories of defenses. However, they require hardware modification to actively emit ultrasound or redesign the microphone layout, so they cannot apply to billions of legacy devices. The signal feature-based defenses rely on the device-dependent nonlinear effects, such as they were focusing on certain frequency ranges or the signal skewness in the time domain. Besides, they are supervised and require attack data collection and labeling efforts for almost all devices. Overall, we summarize the limitations of prior defense. We are motivated to explore why the signal feature-based methods are device-dependent and require collecting a lot of attack data. By partially displaying the spectra of inaudible commands on 24 devices, we can find the different devices will have different characteristics when facing with attacks. One of the major reasons is that the microphone's inherent high-frequency response curves above 20,000 Hz are totally diverse. By contrast, their response at the major frequency range of human voice, which is calibrated to the telecommunication standard, look at this between the red dash, are almost identical. So our basic idea here is to extract the commonality between the audible legal voice commands and then detect attacks as if doing the anomaly detection. This paper proposes NormDetect to achieve the following goals: to instantly protect the billions of legacy devices, to be device independent and don't have to collect any attack data for each type of devices. What we found from our preliminary study for the command OK Google is consistent with our prior analysis of the microphone response. That is, although for each device, the injected inaudible commands may show a variety of features, yet the normal audio that are audible share commonality. Here to quantify the commonality and the variance, we calculate the spectral similarity between two audios and form the heat map of similarity scores. You can see where higher score indicates the pair is more likely. We can observe the similarity scores between the normal pairs are much higher, while the attack and the normal pairs are much low. So our conclusion here is, for the same voice command, there are noticeable differentiations between these two types. However, for the actual system, various speech content is more complex, and there are still two key challenges. The first is a variance challenge. As normal audio may appear different patterns due to the ambient noise, speaker factors, and the voice content, etc. As the figures show below, you can see the legal and the attack audio distributions may partially overlap. The second is the unsupervised challenge. How to reliably detect attacks without any attack data as prior knowledge for training our detection model. The basic idea of our NormDetect is inspired by the autoencoder. It's a machine learning technique that functions similarly to our human brains, which can firstly extract the crucial information and obtain the compressed data. Then it can reconstruct the original input as a learned representation based on the compressed data. The reconstruction error here demonstrates whether the autoencoder can describe inputs well. This feature makes it also widely adopted in the anomaly detection because the reconstruction error can indicate a text from the normal. For instance, in our work, the autoencoder is supposed to well reconstruct normal audio spectra and obtain low reconstruction error. But when facing with anomalies, the model should reconstruct badly because it has not been fed with any attack data for training, thus resulting in high reconstruction errors. Another reason for the autoencoder framework inherently matching the anomaly detection and our goals is that it can be trained only with normal samples using the reconstruction error, particularly given that collecting inaudible voice attack data is difficult and time-consuming. However, making the NormDetect reliably discriminate between attack and normality is still challenging, since there is lots of variance as shown in this picture. We should ensure compactness in the distribution of normal samples to promote differentiation from attacks and that are outside the distribution range. Therefore, we introduce a variational autoencoder structure. Namely, we drive the NormDetect with two objectives. It should well reconstruct normal samples at the same time, encode them to compact Gaussian distributions. It means that our optimization is guided by both of the reconstruction loss and the distribution loss. Moreover, we drive the model to memorize normality by implementing a memory module between the variational autoencoder framework. Each slots parameter of this module is also optimized only with normal samples. During the inference stage, an attack's encoded embedding will calculate quasi-similarity with each memory slot of M, and a memory similarity weights vector W is therefore obtained. Then, the items with similarity scores below this threshold are removed, while those above the threshold will be normalized to the 0 to 1 range using softmax. Furthermore, the original attack embedding is replaced with a Z prime that is very close to normal samples, resulting in a much higher reconstruction error, while that of the normal samples can be still small. For the variance challenge, as we have mentioned that varying factors can result in normal patterns in being diverse, we first address the ambient interference by periodic noise perception and removal, so as to keep different from attack samples that can take ultrasonic transformation-induced anomaly noise. For the variation caused by users' speaking habit, such as speed or semantic pause, we remove those unnecessary silence clips. We also employ length normalization to handle different speech content to 1.5 seconds per frame and apply multi-frame voiding for a reliable decision. After calculating the raw STFT spectrum, we augment the differences between normal and attack samples by proposing two key methods. The first is long-time average normalization, which can reduce the influence of speakers and speech content. And the second is attentive statistic filter, which first splits the spectrum into 128 dimension subbands and assign different weights to them according to the training set and the energy distribution affected by the nonlinearity effects. So our evaluation is here. The NormDetect model is trained by the open source English fluent speech command dataset, and the evaluation data is collected with our displayed setup, involving 7 distances, 24 smart devices, and more than 300,000 audio samples, which are entirely unseen during our training. Overall, NormDetect can effectively distinguish between audible commands and inaudible attacks. So when using NormDetect, a user may be more concerned about its effectiveness across different distances, ambient noise levels, and device models. After experiments, we find NormDetect is highly reliable under varying distances, typical office scenarios, where with noise level less than 50 dB, and protecting mainstream devices as well. Our experiments also demonstrate that NormDetect can adapt to unseen languages, here is Chinese, and speakers. Moreover, we envision that users can register register several utterances to fine-tune the model deployed on their devices in a more customized style. When attacking the NormDetect, an adaptive adversary may try to create adversarial examples that can bypass the detection in the digital domain, and then load it onto the ultrasonic carrier using amplitude modulation. Nextly, it is supposed to deceive and bypass our detection system. Our results show that that despite crafting adversarial examples with full knowledge, NormDetect is still usable. This is due to the nature of unstable ultrasound transformation, which has been addressed by our new work published in the NDSS 2024. Our conclusion is here. We propose NormDetect, the first unsupervised software-based mitigation against the inaudible voice attacks that can instantly protect legacy devices. And the effectiveness of NormDetect is evaluated on the large audible and inaudible voice commands dataset consisting of 24 devices and more than 300,000 audios. That's all of my talk. Thanks for listening.